In this video, I'll be discussing the idea of sets. To motivate this discussion and to come up with and articulate our first set, I want to go back to the 17th century and talk about a man who went by Chevalier de Mer, which translates to Knight of Mer. Now, Chevalier de Mer was a professional gambler. He was a poet, a salon theorist, and one of the games that he played, and he made his money, or part of the way he made a living is through gambling. The game that he liked to play, he would play with one die, six-sided die, and the bet would be that he could roll at least one six out of four rolls. Now, let's stop for a minute and think about this idea of set and the math definition. A set is a collection of distinct objects, and we call those objects elements. And a set can be defined by describing the contents or by listing the elements of the set enclosed in curly brackets. So let's go back and talk about de Mer for a moment, Chevalier de Mer. And many mathematicians just simply refer to him as de Mer. And he is quite notable. I mean, he is credited with really motivating the whole field of probability theory. And it was a game similar to this. And I'll talk more about that later in future videos. But for now, I just want to focus on the idea of a set. So we have this game. We're going to roll a six-sided die until a six is rolled or the die is rolled four times. And there are a number of different sets that we can come up with. But one of the sets of interest is the set of possible outcomes when a six-sided die is rolled four times. Now remember, in the definition of set, we can define a set just by writing out a description of what it contains. And so this set we're talking about is the set of possible outcomes when a six-sided die is rolled four times. The definition also stated that we could use curly brackets and write down all of the different elements of the set. And so when we start to think about this, I'm going to think positionally now. I'm going to roll a die four times, and we could get a 1, a 1, a 1, and a 1. So if I wrote down 1, 1, 1, for example, that would indicate that a 1 was rolled on this die all four times. Another thing that could happen is we could roll all sixes. We could roll a 1, a 2, a 1, and then a 2. So this set's going to be really hard to write down using curly brackets. In fact, we can use the fundamental principle accounting to calculate that there are actually 6 to the fourth power possible things that can happen when a six-sided die is rolled four times. And that's equal to 1296. So if I were going to try to write this set down using curly brackets, I'd have to write down 1,296 elements. Now, we could also refer to subsets, and in this case, a subset could be defined in words as the possible outcomes resulting in at least 1 6 when a six-sided die is rolled 4 times. So again, I'm defining the set by describing the set. So this is a legitimate way to describe the set. And to write this set down, we kind of run into the same problem we had above. I could start to write down these elements. So it could be one element in this set would be 1 or 6, 1, 1, 1. Roll a 6 and then 3 1s. Or we could roll a 6, a 2, and then 2 1s. Or we could roll a 1, a 6, a 1, a 5. I mean, again, there are so many different possibilities here. In fact, this calculation is a bit more complicated, but I'll just tell you there are actually 671 elements in this set. And these are actually, these two counts have a name, and I mentioned this in the descriptor for the section, but cardinal number. So this is the set's cardinal number. And this is an idea that we attribute to George Cantor. So the cardinal number for this set described above is 1296, and the cardinal number for this subset is 671. But let's take a look at a bit of a simpler example. I don't know if it's simpler really in the abstract, but it's simpler in terms of the number of elements in the set. So imagine if we flipped a two-sided coin 3 times. And again, we're going to assume our coin has distinctly different sides. So we can tell which side is heads, for example, and which side is tails. So now if I can define a set as follows. Here's our set. So again, I'm defining the set by describing the set. It's the possible outcomes when a coin is flipped 3 times. That might seem a little vague. Now, let me write this down using curly bracket notation. So this is, and I'm going to call the set capital S. So this time I'm going to actually give the set a name. This set is the set where we have 3 heads. That means the first flip was a head, the second flip was a head, the third flip was a head. Another element, possible element in this set would be flipping a tail and then 2 heads. We could have a head, a tail, and a head. Or we could flip a head, and then a tail. Or we could flip a tail, and then a tail, and then a head. Tail, head, tail, tail. Or I think the last element in this set would be 3 tails. So notice this set I can actually write down fairly easily. One question I might have, though, or we might have, is do I have every element in this set? Have I listed all the possible outcomes? Well, there's 1, 2, 3, 4, 5, 6, 7, 8 elements in this set. So this cardinal number over here is 8, according to the way I've written it down here. But it's also possible to calculate this. This is another situation where the fundamental principle accounting is useful. Since there's 3 different events, each are independent, that's a math technicality, but we'll talk more about that down the road when we're talking about probabilities. But in any case, there are 3 different outcomes we're looking at in a sequence. Flip a coin, flip a coin, flip a coin, and each of those have 2 possible outcomes within each I know I'm sorry, starting to sound a little bit confusing, but in any case, each flip could be a head or a tail. That's two possibilities. We flip the coin 3 times, so there are 2 to the third or 8 possible outcomes, and so our set has 8 elements. Another way to see this, and this is something that I find extremely useful when I'm working on these kinds of set cardinality type problems, or what we sometimes in math we call these counting problems. But in any case, drawing a tree diagram. So in this case, the first flip could either be a head or a tail. The next flip could, if the first flip was a head, then the next flip could be a head or a tail. Or if the first flip was a tail, then the next flip could be also a head or a tail. And finally, you can begin to see how I would fill in this tree diagram, I suppose. And at the end, we see the same set that I've written down up above. 3 heads in a row, a tail and 2 heads. It's in a little bit of a different order, but nonetheless, there are 1, 2, 3, 4, 5, 6, 7, 8 possible outcomes. So the cardinal number of the set I described earlier is 8. There's several different ways you can see that. And we could also talk about a subset of the set above. Let's see. See if this makes sense. So we have a subset of the set before, which I would describe as the possible outcomes where 2 heads are observed when a coin is flipped 3 times. And so again, one of the nice things actually I think sometimes about going into the math notation world is it becomes explicit what we're talking about. And now I'm talking about exactly 2 heads in this case. So that means that either the first 2 flips were heads and then we got a tail at the end, or we flipped a head, a tail, and a head, or we flipped a tail and then 2 heads. So the cardinal number for this set is 3. Now, one of the other concepts that comes up in this discussion, or in this discussion of sets, is the idea of a complement. And I'm going to just put a little C up here. There's a couple of different notations that are used, but this is the one I see. Personally, I see it more often with the C now. The one with the little tilde off to the side. I don't know. It depends, I guess, on the field of mathematics that you were working in. But in any case, the complement of the set above is everything that's in the master set, or the previous set, that's not in A. So A complement is everything that's in the set possible outcomes when you flip a coin 3 times that's not in the set A. And so what would that set look like? Well, we could have 3 heads in a row. We could have 2 tails and then a head and then 2 tails, a tail, a head, and a tail, or 3 tails. And so notice that A an A complement or disjoint, meaning their intersection's empty. And we'll come back. I'm going to talk more about this in a subsequent video. But for now, one last thing I did want to talk about is the idea of probability theory, which is coming up later. But notice that we can calculate the probability of flipping 2 heads if the coin were flipped 3 times by taking the number of ways, or the cardinality of set A, which is 3, and dividing that by the cardinality of the entire set, which are all possible occurrences of heads and tails when you flip the coin 3 times. So the probability of getting 2 heads exactly out of 3 flips of a fair coin would be 3 out of 8. Well, that's it for this video. I'll see you next time.